Hello everyone, today's video is a big one. I did a lot of work preparing it. There are a lot of things I would like to cover today. The video is divided into 5 parts. First, algorithm and methods of PCB design. Second, comparison and testing of LoRa modules. Third, using Unity test module. Fourth, communication test program. Fifth, economic rationality of independent manufacturing of communication modules. Palyonish used modules like this in the circuit. I bought them, but then it turned out that they are not in stock where I bought them. I placed a pre-order and was offered to buy a pack of 80. That doesn't work for me, I need 5 pieces. In general, I found them in a Chinese store here, but I could not buy. Need WeChat, but I could not register there. Need to confirm another user WeChat, and I do not know such. Who can help with registration right? Because I have previously made a circuit board where you need such an arrangement of castellated holes. I could not find similar ones. After all attempts to purchase such a circuit, I decided to design it myself. The circuit must be pin compatible with this one, so that I can solder already ordered new versions of the Palyonish circuits. Of course, any project should start with the search and preparations of the necessary information. I chose the Semtech website as a source of inspiration. It has a lot of useful information. On this site, I am interested in schematic diagrams, recommendations and calculation methods. I will say at once that they are not useful to me, like this one, which very briefly shows how to experimentally calculate the matching device with antenna feeder device. Of course, I did not use this technique because it would take a long prototyping process, so I turned to the examples of the debug boards from Semtech, from where I took the basic topology of the devices. There is also this document from Semtech where there is an overview of the boards from the developers. I am interested in the 433 MHz circuit, and here is a link with the name of the device. You can choose that suits you. These schematics and Gerber files are in archives. Here is the archive, and here in the archive everything is. Here we can see an example of tracing and schematics diagrams. It is certainly not a 61278, it is a 61276. The chips differ only in the allowed frequency bandwidth. The datasheet shows that my S61278 works at these frequencies on the LF pins. There are block diagrams and detailed description here. I'm operating under the assumption that the input impedances of the S61276 and 1278 circuits are identical. That means that we can safely take this part of the matching device from the example. We don't have to think and calculate anything. If you want to make the matching device yourself, I will leave a link to the document with detailed instructions of the description. All examples of matching device topologies are made for a certain track width. Different tracks have different impedance. Semtech has fortunately produced this document of what layer thickness they used. In this case, the prepreg is 0.2 mm thick. Our PCB manufacturer will have a different prepreg thickness and a different material. So now let's find our wave impedance of the track Semtech used. I'm measuring the thickness of the track. I open the extension, I enter this thickness here and get a value of about 50 ohms. Great, so we'll use this value to calculate our manufacturer's track width. I will order on GLC PCB, which I recommend to you. I open the calculator, select the used fiberglass and the desired impedance of the track. At the output, I get the desired value. This is what we will use when tracing. I used EasyDA for drawing circuit diagrams and tracing. While drawing, I was not sure that the circuit would work, so I made 3 versions. In the end, all 3 worked. Tests will be in the next section. For example, let's consider Camar version 0.1. This is a schematic diagram. I have not invented anything new here. Here is the circuit I took as a basis. The only difference is that in my versions on the chip there are no high frequency pins RFO HF and RFI HF, which influence the topology. The list of all used elements is also in the archive. The ratings of all elements I also took from here. All files with my project I will leave in the archive under the video. If you plan to repeat this scheme, I recommend to consider elements of greater type polynomial. Such small elements are difficult to solder. In this case, we are not interested in the actual transmission power. I want to answer the question first and foremost with measurements. How well the circuit transmits and receives relative to my other circuits and the factory circuit. On the basis of this data, we will choose the leader of reception and transmission. In addition, I want to draw your attention to the fact that the figures given are relative and valid only under these test conditions. In other conditions, for example of other antennas, the results may be different. In addition, we need to compare the differences between circuits bought from different sellers with different labeling. Are there any differences? If so, how significant are they? This is what the imaginary test bench looks like. The circuit under study is connected to this microcontroller. Identical antennas are soldered on all circuits. When the button is pressed, the circuit switches to the receive or transmit mode. We will receive or transmit to this vibrator. It will be our reference. During testing, I will try to keep the mutual arrangement of antennas for more accurate research. It should be noted that antennas with different polarization are used. On the Camar schemes used antennas with circular polarization and on the sample scheme horizontal. It should be said that due to the different polarization, the signal will differ by about 3 decibels. I will output the investigated information to PC via UART. On the left is the window with the information of the investigated circuit. On the right is the reference circuit. The principle of research is simple. Turn on the reception of the circuit under study, the transmission of the reference. Then the opposite received figures for each circuit are entered into the table. On the basis of this data, we will draw conclusions. Developed 3 versions of the circuits, soldered breadboard wires to castellated holes for testing. I've tested them all 3 of them are working, but not all of them work equally well. There were some flaws. During the test I found errors in the Camar version 0.3 circuit. I corrected then by soldering a short circuit instead of capacitor C6. Apart from the difference in topology, each PCB version is soldered on a different chip bought from a different vendor. I have 3 chips. Here you can see that the name is the same, but different font and font size. I assume that these chips are from different manufacturers, regardless of the name. Well, apart from the labeling, the price is also significantly different. I will demonstrate the test method on the example of Camar version 0.1 circuits. I connect the circuit under test to the microcontroller according to the diagram on the screen. I switch on the reference transmitter for transmission. On the left side of the screen are numbers indicating the quality of reception. Now I do everything the other way around. I put the reference transmitter in the receive mode and the circuit understudy in the transmit mode. Read the numbers and enter them in the table, and so on for all circuits. There is nothing complicated. The project with the source code for research I will leave as well in the archive at the link. Of course, I will not miss the opportunity to test similar algorithm factory circuit bought on AliExpress. The results will also be placed in the table. Let's analyze the test results. RSSI is an indicator of the strength on the received signal. The higher the value, the better the transceiver works. High values show that the scheme is correctly designed. As you can see, the most successful were Camar version 0.3 and also not worse were the schemes on chips RFM98 bought on AliExpress. According to the figures obtained from the tests, it is clear that the Camar schemes version 0.2 are suitable only for reception. Looks like I made a mistake somewhere. Well, it is not so important. Just for such a situation and developed several versions of schemes. When writing code, I often encountered hard to trace logical errors. That's why I started studying various methods of writing code, and I found a great book, Test-Driven Development. If you often encountered logical errors, I recommend you these books as well. After applying the principles described in these books, the program became more reliable. First, I implemented a test application to test a connected LoRa module. It checks the correctness of the microcontroller unit configuration of operation, values of register after reset, correctness of FIFA buffer write reads, SX1278 configuration to accept, configuration of SX1278 of transmission. This is necessary to check the operability of the newly soldered LoRa module and the correctness of the configuration of the control microcontroller STM32. I open Cube IDE project with test application. On the left are all connected libraries. Here you can see that the Unity testing library is enabled. I mentioned the book by James Groening earlier for a reason. From this book I not only learned about the concept of test-driven development, but also about such a great test harness as Unity. James Groening's book gives detailed instructions on how to apply this harness to driver development with detailed examples and explanations. I have just started learning this concept, and this is my first program, for which I am testing using the methods described in the book. Let me say right away that I use it in a different way than the author of the book suggests. From the very first sections of the book, the author emulates a real device. I do not like this method because during emulation I can make more errors, which I will not notice until I write the program into flash memory. Therefore, I have made some changes to make it easier to work with the Unity library. I write the used Unity functions to the STM32 memory, and I test directly on the target platform with the subsequent output of debugging information on the PC in UART through such TTL converter. I display everything on the monitor using a free program PuTTY. In the description, I will leave a link to the file with instructions on microcontroller configuration in Cube MX and PuTTY settings. Let's return to viewing the files to be plugged into the project. The testing functions are defined in the Test Unity project catalog. A number of functions are defined in the start test.c file. Run all UART tests, starts all the necessary tests. The putchar function is used by the Unity library to output information. Here, the Unity output is sent to the UART using the HAL UART transmit function. Also in the program to output text message to UART is used function printf. For its proper operation implemented macro putchar prototype. An example of the implementation of this function I took from the examples from ST. Test Unity project contains files with tests for each module that I considered necessary to test. Testing is very simple. Test functions of setting all those parameters that we have configured in Cube MX are started. Then the tests are run all UART tests. This procedure runs a number of tests. UART init start is implemented in the test usart directory. Here we simply test the baud rate. The SPI test checks the contents of the configuration register status register 1. In the case of a different SPI configuration, we will receive a message in the UART with a line of code that has not passed the test. A test GPIO checks the configuration of the output input ports for operation with this LoRa circuit. Since this video is about LoRa in detail, we will look at the LoRa module test functions. LoRa reset reg conf checks LoRa register values after reset. LoRa reset FIFO checks the FIFO buffer to see if it is working, written write capability and the integrity of the written data. LoRa FIFO write checks that the FIFO buffer is readable and that there are no write overruns. LoRa init checks the LoRa static configuration register for reception. LoRa rx cont checks LoRa signal receiver functions. LoRa tx init and LoRa checks tx check the setting of static configuration register for transmission and also the data to be transmitted. LoRa tx cont transmits 6 packages. We can see them on the SDR receivers, SDR waterfall. In this context, the purpose of the tests is not only to check the performance of LoRa chips, but also to preserve a working solution. In case of changes in the driver code, we can always run tests and find out what the problem is. Properly written test will show what changes made caused the loss of functionality. Running test is very simple. I connect devices according to the scheme. I start PuTTY and configure it to the settings similar to those made in Cube MX. I flash the microcontroller and the tests are running. After that, the PuTTY window shows where the error was. In addition to the output of debugging information in UART, tests include the start of the module to receive and transmit. Here, already without auxiliary devices, cannot do without. I set breakpoints. When receiving, I use a device called Atsasimba, which I designed is one of my old videos. I switch it to transmit and look at the received packets in the debugger. I switch to transmit mode in the debugger and observe that the circuit transmits. Some packets on the waterfall SDR receiver. I think for initial familiarization with test-driven development and Unity, these tests are enough. The project with the test will be in the archive at the link. In this part, we will consider the code we used for research of communication quality. All three homemade LoRa modules have different circuit diagrams and topology, which influenced the program code. We took these differences into account by means of conditional compilation. Depending on the scheme used, we can set the flashing variant by changing directives in main point H. Changing directives leads to change in the compiled code. In the SX1276 LoRa init procedure, they are placed with conditional compilation. It is due to the fact that different versions of CAMAR use different radio frequency outputs from SX1278 chips. In addition, different switching principle of matching circuits is used for receiving and transmitting. In general, the SX1278 circuit has a circuit selector, pin RX-TX FR mode, but not everywhere involved this pin. In the circuit CAMAR version 0.1, I did not use it. To control the circuit selection, I used the microcontroller output, which is connected to DO3. This entailed changes in the control program. Here in the function mx_GPIO_init for CAMAR version 0.1, the settings of the DO3 pin of the master microcontroller are changed. The state of this pin is then changed in the SX1276 LoRa set op mode procedure. There are no other code changed for the various CAMAR circuits. The press state variable is used in the main loop of the program, and we change it when the button is pressed by interrupt. Based on the selected mode, we will perform reception or transmission. The main functions used here were tested by the application from the previous section. In addition, we have tested the hardware, and now we are sure that all circuits are working. Further, everything works very simple. In the receive mode, we configure the LoRa circuit with the init_rx test mosquito function to receive. Further in the loop, waiting for a positive state of the output DO0, which will indicate that the packet was received. After calculate and output the values of the quality of communication in the UART. In the case of transmission, the microcontroller is initialized for transmission with init_tx test mosquito. After the tx test mosquito function, a packet is sent every second. If you have studied the test application carefully, you will not see any differences between these functions and the functions from the test application. Only the order has changed. Let me point out a place that I did not understand. In init_rx test mosquito, I repeat SX1276 in it, despite the fact that I had already initialized it in main. Without reinitialization, the program did not work as expected. I have not understood what the error is. In general, this is not the topic of this video. I will leave the whole project with libraries in the archive at the link. Let's look at the cost calculations. Here is the cost of LoRa circuits on LCSC and AliExpress. As tests have shown, there was no significant difference in transmission quality, but chips bought on AliExpress are much cheaper. So it makes sense to take them where it is cheaper. The table below shows the price of one Camar circuit on different chips, without taking into account the work. The bought Camar version 0.3, which showed the best results on tests, is highlighted in green. On the right is a comparison of the cost of Camar version 0.3 without taking into account the work, and the LoRa circuit bought on AliExpress. This circuit showed good results on tests. As can be seen from the comparison results, even without taking into account the time spent on the assembly of circuits bought on AliExpress is more favorable than homemade. I will say that soldering such small parts does not bring any pleasure, so I recommend you to save yourself from this ordeal and buy factory-made ones. Factory modules turned out to be as good as homemade ones, and their cost is less than homemade modules. Therefore, in most cases, it makes sense to use ready-made modules. If you are still going to solder your own boards, I recommend to take Chinese analogs. They are much cheaper with the same quality of transmission reception. That's all for today. Thanks for watching. Subscribe to the channel. See you later.